Okay, so good morning, everyone. How are all of you today? Great. Oh, I like that. Great. It's a beautiful day out. Look, it's a beautiful day. So, I'm not really feeling the love. I don't know why.
You can always tell that there's like an accounting test coming up in bio classes because always do like for one attendance drop. I'm sure people seem a little distracted for some reason.
So, what we're going to do is we're going to continue on our conversation from last class because we set some stuff up, but we really didn't see how it works out in Excel. So before we jump to the computer, what did we talk about last time? Confidence interval. So tell me more, Cassandra. What's a confidence interval? Mm-hmm. Yep, so exactly when we take a sample, we get a sample mean. That's our point estimate, our best estimation of what's going on. But we recognize that what's actually going on is it's a little bit lower, it's a little bit higher. And so we want to try to get an idea of the range that the true population mean could fall on based on that point estimate. So in other words, we get a margin of error, and then it sort of goes around that margin of error. Right, and I gave you an equation for confidence interval. Remember that equation is.
Yeah, I can't really say it, but it's the minor of x.
X bar is what we always call it.
X bar plus z.
Plus z? Plus or minus.
Plus minus z. Delta.
It's a z alpha divided by 2.
Divided by 2. In parentheses, you have sigma over square root of n.
Exactly. Now that alpha divided by 2, what does that mean? I thought I heard someone say something over here. Oh, in the back? I can't hear you. Oh, I still can't hear you. The margin. So this is the margin of error. This whole thing, that's why we add and subtracted from our mean to get that range. But I'm talking about just the alpha divided by 2. What does the alpha represent? Yeah.
Remind me again of your name, too? It's been like, come on, this happens every Tuesday, I always forget. You give me this look that I should know it. So I'm going to call you Tim. No. I don't remember. Anisha. Oh, it was at the top one. Okay, Anisha, sorry. Last time that will ever happen at Aurora, I promise. Anisha. Well, what were you going to say? What was that, Anisha?
The case of not capturing the true population.
Exactly. So that alpha represents the chance that we did not capture it, that we sort of, missed it essentially. Which means if the alpha is really small, that means a pretty high chance we got it. If the alpha is pretty big, that means it's a relatively small chance we got it. Of course, in statistics, relatively small means only a 90% chance. Right? We try to, because we don't bother with stuff that's like 70 or 30 or 50. That's like, what's the point? So exactly, that alpha represents the chance that we missed it. Why do we divide it by 2? Let's imagine you look at somebody and you want to guess that person's age. You can either be what or what if you are wrong. Too high or too low. So similarly, we divide by 2 because we can make an error. We can say that the true population mean is below our lower bound, or the true population mean is above our higher bound. We are either too high or too low. So we split that mistake into two sides of the tail. Two sides of the distribution of the two tails. What's the z value? Give you a hint. Do you recall we talked about this last time? Remember this? Excellent. So then you can tell me what the alpha is for each of these four. 0.1, 0.05, 0.01, and 0.01. Excellent. In other words, the chance that we're making a mistake, right? Between 0 and 1. Well, then what are these z values?
What do I represent?
It's sort of like it's a standard deviation thing. And you just sort of, and I'll show you, I'll hopefully give you an illustrative idea. So I want to see how much I remember them. 1.645, 1.960. Now I remember 2.576, right? And 3.12, damn it, 3.291, right? Okay, I'll give myself a 90% on that. But you never have to memorize them because I'll give them to you. Right. But you can also find them in Excel.
So I kind of gave that to you last time. We talked about that, and you look up for any particular
Alpha, it's a two-tails test. I guess I'll be using this z-score. So keep in mind that alpha divided by 2 is not part of the equation. It's a notation for z. It tells you which z to use. So this whole thing right here should be one particular number. Don't like take this number and then like multiply it by 0.05 and then divide that by 2. You're doing it wrong. This is one thing. Any questions?
So now I have to admit something to you. I kind of lied to you when we did the empirical roll. Sorry about that. Everyone lies to you on the empirical roll, though. It's not just me. What was the empirical roll?
What was it? Your name is Patrick?
No. Charlie. Well, you have the consonant. All right.
About 68% of observations within 1 standard deviation.
Mm-hmm. So 68% are in 1.
95% within 2.
Mm-hmm. Excellent, yeah. And we derived it, right? So we took...
we did this right here where I put in negative 2, for example, and a positive 2. And then we used the formula, right, the normal standard. So I put in equal normal standard for this, made it cumulative, copy and paste that over, highlighted where to the center equals one thing minus the other, and got 95%. Right? But I That's also really right. You saw that before I hit the percent button. Is it 95% exactly? No. We got some junk here. What was junk? What's the rest of it? There it is. Look at all that. It's not 95 exactly. That's because it's not exactly plus or minus 2. That's the lie. The empirical rule, we say it's a rule of thumb. It's useful because 2 is easier to remember than what it actually is. Not plus or minus 2, plus or minus 1.96. If you put in 1.96 here and negative 1.96 here, still not exactly, but a hell of a lot closer than it was before. Right, now we got zeros out to 3 decimal places for the percent. No, it's not going this way. Much better. So hopefully by bringing this up, you get a little bit more intuition as to what this 1.645, 1.96, and so forth, 2.576, what they represent. Okay. So last time.
Can I see the formula for that?
Yeah, sure. It's just what we used before.
Oh, you didn't change anything with the decimal?
No, the only thing I changed was I made it 1.96 rather than 2. Yeah. I guess I added some decimal. So we also discussed how we would use this using this confidence interval. The good news is this thing, this part, not the whole thing, but just this part, the margin of error is built into Excel. So while I give you this information, because it's nice to have, and you know where it's going, where it's coming from, it's also built to Excel, which is quite nice. Now Excel likes it when you put in one function, one value, and then outputs another one. So you can put in this huge long equation, I should say, this huge long function, and then it only wants one number to come out. It makes sense from the computer standpoint because this is a particular cell, so that reflects one and only one number. But a confidence interval is not one and only one number. How many numbers is it? How many numbers is a confidence interval? 2. Right? It's 2 numbers because you need a lower bound and an upper bound. So Excel doesn't function very well with that. It likes to only output one number, so that's why it gives you the margin of error. And you have to do the actual interval, the plus or minus the mean, by hand. And by hand, I mean you have to tell Excel minus the current mean. So like, don't get too upset, you have to do it, it's not a big deal. I know you're able to jump this under, there we go. So let me start what we're working with. I have, this example. DealWorks at Friendly Friends, a toy company. And every few years, the company makes slight alterations to its teddy bear, its #1 seller, makes slight alterations to it. They might swap out a green hat for a red hat, or maybe they make it a little bit more fluffy. Something that doesn't radically change it, but still gives it, still makes it slightly different. They're always trying to improve themselves at Friendly Friends. Plus, they also have to adjust for changing market conditions as well. I'll keep that up there. So they need to know, now that they have this good idea as to what to do, now that they made it, now it's going out, they need to figure out how many of these bears to order. And so Theo maybe sets up some focus group and says, we'll say it's 341 people, and tries to get an idea for how much people like the bear. And let's imagine he gets a particular. He estimates that based on that 341,
the average number of bears sold will be 413,512. And exactly how this translates into this is a bit tricky given my scenario, and I'm trying to do one that's relatively straightforward. So this isn't a perfect example. In practice, you would probably get a proportion of people who like it and then extrapolate. So maybe 80% of people like it, or 20% of people like it, and then how many customers do we get, and then we'll multiply that by 0.2 and get this. But I'm just trying to keep it, I don't want to work on it too much about it, just getting us familiar. They also know that because the alterations are rather minor over the years, that the standard deviation of how much they sell, they readily assume that's constant for good reason. In other words, they know the population standard deviation, sigma, which I said was 15,386. So, here's what I want to do. We're going to set up Excel. So we have various thresholds, various alphas, 0.1, 0.05, 0.001, 0.01. I don't know what it is. There we go. And 0.0. So these are going to be our alphas. And we'll call them alpha Z, the Z score. We will, as you know, be calculating margin of error, and then we will find a lower bound and an upper bound. And then for reasons that will become clear, we're going to reference a value n. And I just want to make that nice. I'm going to do a box line. And we decided that is 341. We decided that too. So, here is where I put the margin of error that we're going to use Excel to calculate based on this information and the information I'll provide. I put in an n over here because later I want to change it. I want you to see how it changes and then changes, so that's why I set it aside. And then we'll, by the lower bound, we'll take the margin of error and we'll subtract off the average, subtract the margin of error from the average, add the margin of error from the average, and thus get a range. So our first step, and we're going to start with 90% confidence. We need to figure out what we put into, what command do you think we use? What command do you think we use? Confidence. Ah, yes. So many of you might want to use margin or error because you calculate the margin of error, but Excel knows you calculate the margin of error to determine confidence level. So we'll say equals confidence. And note that we have actually three options for confidence. I use this one in the notes because this is the old one. I need to update my notes. So you'll later see this as confidence.norm because that's what we want to use, confidence norm for a normal distribution. You use this if you know the population standard deviation. Confidence T is something we'll talk about later in this class. We'll stick with confidence norm for now. Confidence norm wants us to use 0.1. First thing that we have to put in, alpha. That will be 0.1. So we're just going to reference alpha. What's the next bit of information we have to put in? Standard deviation. What was our standard deviation? 15, 3, 8, 6. Thank you. And finally, what's our size? 341. I'm just going to make that reference there. I'm also going to hit F4 because I want to make the reference A so that I can change it. Everything will update. So I'm thinking ahead. And B, I'm hitting a 4 because I want to lock it. So when I copy and paste this down for the other thresholds, I won't, I won't lose that reference. It won't come down with it.
And then you can hit enter or close parentheses and hit enter. Oh, let's add a comma.
Here we go. And we got 1,370, roughly. Does everyone have this? What do you think will happen if we copy and paste this down, changing our alpha scores? What do you think will happen? Anyone?
It will be smaller.
So you think it'll get smaller? Let's find out. Nope. It got larger. Why did our margin of error increase as we reduced alpha?
Our confidence level.
So?
So the higher the confidence level, the more margin of range
Exactly. It makes sense that if we have this range at 90%, there's a 90% chance we captured the true population means. That if we want a 95% chance, we're going to have to make our range a little larger to capture the things that will be on the edge. We'll make a 99% chance a little bit larger, a 99.9% chance a little bit larger. So we have to increase our margin of error if we're going to be able to make a claim that we've captured the true population means, or a stronger claim we've captured it. So that's why our margin of error increases, almost doubles, right? More than doubles in size.
Now let's find the lower bound. What is the lower bound of this? Anyone?
So now we're using this part right here, the plus or minus. Though I think in your notes I say minus plus because
I wouldn't say it. I mean, I guess minus plus makes more sense because you would do the minus part for the lower bound before you do the plus part for the upper bound. And I'm always just used to seeing plus or minus. See that?
Is it a 450,000 factors all minus? So it doesn't take the
It's my
415, 500 from here.
And then I can copy and paste it and put it in the upper bound because I change that minus to what? Plus. And that's my upper bound.
And so it's like there's a 90% chance that we will sell between 412,141 units and 414,882 units. With some obvious, because you can't sell half a unit, so we round it a little bit. Okay. Now, what can you do with this information? Well, this is where the business part of business statistics come in. So it depends on what the company wants. You give them numbers to work with. The statistician gives them numbers to work with. And then the marketing people might be like, well, maybe we want to go a little bit on the low side. Because, maybe we can, if we run out, we could generate some buzz. But we don't want to have too many because maybe it looks like trash. On the other hand, maybe you want to go on the high side. You want to say, look, it's really, it's a competitive environment. You can't rely on generating buzz because you run out of stuff. If we just really need to sell all the ones we can sell. And I don't want to take a risk on trying to generate some buzz because we don't get anything. So it gives you some numbers to work with, but the point is you now have some numbers. You now have some idea as to where to go. Maybe just want to go with the middle. Maybe you want more information. Maybe you say, okay, that's 90%, but there's a 10% chance that it will fall outside of that range.
So let's go for the other ones.
Note what happens as we go from a 90% or an alpha of 0.1 all the way down to a 99.9% or alpha 0.001, we have a larger range, right? These numbers get smaller, these numbers get bigger, it's larger and wider, just like we talked about. Let's say, look, the likelihood that we'll sell over 416,254 units is really, really, really unlikely. It's actually less than a 0.1% chance, right? Because it's more than that, so it'll be half of that. So if you want to really make sure that we have enough units, 416,253. Maybe the units are really cheap to make, so who cares if we have extra? At the same time, maybe the units are really expensive to make, and we really don't want to gamble having extra units. We'd have to destroy them or get rid of them somehow. And then we might want to go for this one with a lower bound. It's really likely that we won't get less than this. It's really likely. So just to make sure we don't have to have anything extra, we'll use 410,770. Any questions?
Okay, sure.
Of course.
Let's check that. What's this big numbers? I'm not going to show you
The upper bound, because the upper bound seems the lower bound, but these are additions rather than subtraction. Any other questions? Well, let's play around with this a little bit. Let's change n.
And we set up, recall, at 341.
What happens, do you think, if we make n really small, like say 25? What do you think will happen with this ME? Will it increase or decrease? Will it increase or decrease? It will increase. Why do you think it increases, CJ? I'm sorry, I couldn't quite hear you.
They're more sure about the
We have more information. Exactly. I'm taking away some of that information, and unsurprisingly, the margin of error shoots way up. Any questions on that? Yeah. Joyce. What? How did you get this? What does LB stand for? Okay. Lower bound. Excellent. So this is, in other words, the lowest that could be in our range. So I just took our average and then subtracted this value from that average. Yeah. There's our average, and then subtracted off B2.
And that's UV stands for upper bound. Same story.
You locked it, right?
Yeah. I have to, right? Because I'm driving it down.
You did F4.
Yeah. Any other questions?
Okay. Yeah, you really get a sense. Let's check out a little bit more than the organization and try to because I'm a good idea for this goals.
Yeah, you get a really great sense of how important sample size is. Because we went from 341 and we had a pretty narrow range to now when we go to 25, the range is really a lot bigger, right? This is actually a range of over 20,000. So, on one hand, clearly this indicates that larger sample sizes are better. But what's a problem with larger sample sizes? What's the problem? I'm not talking about in the statistics. In the statistics and the math, larger sample sizes are always better. I'm talking about more everyday stuff. Anyone? Yeah, Rolando. Yeah, it's like it's harder to get that sample. Did I really need to interview 341 people? Is that really that valuable? What if I only interviewed half those people, which would save a lot of money and effort?
Wouldn't I still get a pretty good what's half of 341? That's right, 170. That's still pretty good. Did I really interview all those people? If only there was a way
I could figure out that maybe for any given margin of error, at a particular confidence level, knowing the standard deviation, I could find an optimal sample size. I could find a sample size that is no larger than it needs to be to achieve a particular margin of error. How would I figure that out? Let me write down optimal sample size, which is the same thing as the minimum size needed to get desired margin of error.
In other words, I have a margin of error, I have a confidence level, I have a population standard deviation, sigma. I want to know my n. How do I figure that out?
England? Yeah, Orlando?
Just plug in. This is a desired derivatives for application that solve for sample size.
Oh yeah, excellent. In other words, let's do some algebra. All right, fun stuff. Excellent. So how would you isolate n in this? Want to give me the first step? Divide by z. Okay. Great. Then what? Multiply by okay. Does this bring up some fond memories? Great, we isolated sigma. Is that what we want to do?
You multiply both sides by square root of n. From the beginning, like from just the first equation. You just multiply both sides by square root of n.
Oh.
And then you divide both sides by root of n.
That might be a little easier, yeah. In other words, swap square root of n and me.
And then you square both sides and isolate.
That is a little faster. So here we have z alpha divided by 2 sigma over me. And then as noted, square both sides. Z alpha divided by 2 sigma over me squared. Everyone follow that?
Somebody remembers this algebra very well. This is sort of satisfying, isn't it? So it's finding the fastest way to do it. Followers?
Yeah.
Yeah, okay. This is like I don't know, I like talking about those. I love finding out the fastest.
But we don't need to do that, that's what I can't.
What do you think?
I mean, you said that everything is going to do with X out.
So some things actually most things are going to itself. That particular equation is not. I will give you that equation, but that, any equation that's not built to Excel, I give you, all these have that formula. Google Sheet. But most things are, some things are not. It's important we know where it comes from, so we have to make sure that's what's going on. So let's go back to our friend. I don't think you need into the top 340 people to get that number. You know, what if all we want is like a margin of error that's no, I'm sorry, yeah. Just the whole thing. Yeah,
maybe I should go over it in black. I feel like my black is very clear. I was trying to mix it up because I get tired of the same color over and over again. But maybe that was foolish of me. Black is the new black. There it is. So, hopefully my superimposing over red doesn't make it even harder to see. Is that better? Does that work? No. Okay. So, let's work with this a little bit. I want a margin of error of the value. I have a standard deviation or small sigma. I have a desired t-score. And then I want to know n. So our sigma just really hasn't changed. We're going to still work with the same sigma that we were working with before. Which I believe was 15,386. And we have a z-score. We'll keep it as, let's do 1.96. This is the z-score. Let's imagine we want a margin of error of no greater than 5,000. How many people would we have to survey to get that? So, how do we figure that out? Okay, on this floor. You have to start with that. Start with open parentheses. How would we figure that out? What do we have in our equation? I'm going to print it up. Think about it. How do we figure out n? Okay, great. So what do we do? Yeah, that's like we do there. Mm-hmm. Excellent. So of course, if you don't know, that's 6, so we go with the carrot thing, power of 2. Okay. Did we need to survey 341 people if all we want is a margin of error of 5,000? No. How many people do we need to survey? 36. Yeah, what the fuck were you doing? But that's technically not the case. 36? Why did you say 36? 37. Why is it 36 and not 37? Why is it 37 and not 36? I'm sorry, what? We need more than 36. If we put 36 in, if we round it down, then our margin of error would be a little bit greater than 5,000. We wanted a maximum margin of error. Minimum sample size. The minimum sample size needed is 36.3767. Obviously, we can't have a sample size of 36.4, so we need to round up. And one more observation, not really a big deal. Always round up.
Why do you do it? Bring it in on this people into the headquarters. Take everyone's time. You only need to talk to a few dozen. And note what happens if we change the margin of error. We say, maybe we want a small margin of error. Will this increase or decrease?
Well, and increase or decrease if we reduce the margin of error? It should increase, right? Because margin of error is the denominator. So naturally, if we want something tighter or we need more information, then indeed that's what happens. It goes up to 100.
Goes up to 102, actually. There's 101.04. We got to round up 102.
Any questions? No. Great. Okay. So all this is using z-scores, which assume we know this value right here, our sigma. But sometimes we don't know the sigma. In fact, often we don't know the sigma. We're looking at something completely new. Or maybe we're changing the bear quite a bit and we can't rely on old information. So we have to do something a little different. We have to rely not on sigma, but S. What is S? We talked about it before. Sample of what? What of a sample? Population sample. I'll give you a hint. Sigma is the standard deviation of the sample. I'm sorry, sigma is the standard deviation of the population. This is standard deviation of the sample. So in other words, we always have S. Right? We don't always have sigma. We don't know always what's going on in the big picture. In fact, rarely we do. But we always have S. We always know what the standard deviation of the sample is because we have all the observations. We have all those individual observations. We can figure out the X bar. Why can't we just figure out the sample with S, standard deviation? So we always have that. We, of course, always have this. This doesn't change. We are going to reflect the fact that this is not a typical confidence interval. This is an estimated one. So we'll throw a little hat on it, I guess, to indicate that it's, I don't know, is it a dunce cap? I'm not really sure why we do that. That's just a way to remind ourselves that we are not knowing, we're not using a regular z-score. We have to use something a little different. We have to use this P alpha divided by 2. We're using what's called the student's t-test. I also like to put little indications. This is the confidence interval X bar, whatever.
Someone's seen this kind of thing before? Has anyone ever seen a t-test before or a t-distribution before?
So, when we don't know sigma, we don't really know what the shape of the distribution is. Remember, the shape of the distribution is defined by its average and its standard deviation. If we don't know its standard deviation, we have to rely on an estimate of it. And that estimate is S. Okay. But which do you think has a more accurate S, a more accurate estimate of sigma? A sample with a lot of samples in it, with a lot of observations in it, like maybe 1,000 observations, or a sample with like 10 observations? 1,000 is more accurate. Why?
There's more observations, so you have the opportunity to have the change an outlier, 10 observations, and that's
Yeah. In other words, you have more information, right? So So assuming the sample wasn't biased in any way, or screwed in any way, more observations mean more information. So our t-distribution looks like a normal distribution, but it's a bit flatter to reflect that we know less. And as we get more information, as our n value increases, then it begins to look like a regular normal distribution that we know and love. It's really a family of distributions where t depends, the t-score depends not just on alpha, still depends on alpha, and on df. Does anyone know what df stands for? df stands for, I think I heard it, degrees of freedom. What is df equal to? How do you determine the degrees of freedom? So there's no complicated equation here to determine the degrees of freedom, to determine how much information you have to work with. You just take the number of observations minus 1. Any questions? Let's take a moment and appreciate why you subtract 1. Why not just use n? Why not just subtract 1? Keep in mind the context. We know something about these observations. We know something about the sample. We know the sample average. Let's imagine I had a sample size of 4. And I didn't know what any of the values are. But I do know that the average is 6. Now, could I put any 4 numbers in here and get an average of 6? Anyone? Could I put any 4 numbers in here and get an average of 6? Drink some water while you think about it. Yeah. So I can put in 0, 1, 3, and 9 and get average of 6. Oh, that has to equal 24. So I can't put any 4 numbers in. Right, I can't. But I can't put any 3 numbers in, right? I can put in 90, -2, 8.5, and 3. Oh, sorry. I can put in, I can put in these 3, right? And then this one I can't decide anymore. This one has to be such that when you add these 2 together, then you have to add this one together, and that equals 24. Does anyone know why you said 24, by the way? What? It stands for, exactly, self-correct. So, in other words, I can't vary these values by 4. I don't have 4 things I can vary. I have 3 things I can vary, and the 4th one is going to be locked in. That's why we take n minus 1, because that 1 reflects what we know that locks in the last variable. There's versions of this too, where like sometimes you're working with 2 sample averages, and then your degrees of freedom are the combined n's minus 2, because you have 2 averages that have 1 locked in values. So they've been locked in 2 ways. Any questions on that? So, because t depends on 2 things, on an alpha on one side and on degrees of freedom on the other,
we don't have a simple table for t. We have a really big table for t. No, you do not have to memorize this table. I'm going to show it to you though, so you can appreciate, and it'll help you get around. This is the table. Really cool. Crap. This is a lot of numbers. No one memorizes these numbers. No one memorizes these. But let's appreciate what the table is showing us and zoom in. Hopefully you'll get some intuition too as to what exactly we're seeing. I zoomed in a bit too far. Here we go. So for one, there is our 90 and 95% confidence levels that we know so well. I marked them too in pencil because when I scroll up, I still want to know what column I care about. Note as well that these are the very familiar ones we've seen for the z-scores, 1.645 and 1.96. And those matter for degrees of freedom equal to infinity. In other words, if you have so many observations, so many degrees of freedoms, the difference between the t-score and the z-score is 0. Because if you're infinite degrees of freedom, you have a normal distribution. You don't have a t-distribution. You have just a standard normal distribution. It's when we, of course, you have infinite degrees of freedom. As we go, let's take a look. Here we go. This is pretty good. Note as we go from the infinite to 1,000 degrees of freedom, this increases also slightly, from 1.960 to 1.962. And then as we go to less fewer and fewer degrees of freedom, the value increases. At 60 degrees of freedom, it's 2 even. At 30 degrees of freedom, it's 2.042. At 25 degrees of freedom, it's 2.06. On and on and on and on, up and up and up we go. It's really interesting at the low values. That's not really that different. At the low values, it's pretty different. 15, 2.131. 10 degrees of freedom, 2.228. 2.5 at 2.571 at 5 degrees of freedom. If it goes up to 12, would you only work with 2 observations or 1 degrees of freedom? That's ridiculous. Don't work with 2 observations. That's a ridiculously high score. But this sort of illustrates to you what's going on. As you have less and less information, then the math suggests you know less and less, and so you have to cast a wider net because that distribution is flattening out. That distribution is just flattening out. Any questions so far? Did you nod your head, CJ, or were you nodding your head in agreement that there are no questions? That's a confusing nonverbal signal you sent me. Now, looking up this table is kind of a pain in the ass. I like showing you the table, but it's more fun to use Excel to find out what t-score you need. It's more fun. So, to show you how this works, this was, where's my chain? Oh, there it is. That 95% confidence, 15 degrees of freedom, 2.131. Let me show you how to find that in Excel. It's a lot faster than looking at some dumb data. This is just to use it. So it's a pretty straightforward thing. In fact, we'll actually even use it at 5, 15, 16, 17, 18. Give us some nice reference. And we will type in t.inv.2t. And that command will, of course, be on your exam, so you don't have to memorize it. And we're going to do it with a probability of 0.05. And referencing A15. Was that A13? A13. So, when we turn off the, what's it called? Formulas, we get 2.31. 2.131. Just like we got on the table. And you can double click it and you can see
How it decreases as we get more information. As we get more information, we can confidently make the interval smaller.
yes, Anisha. This.
Double 0.05.
I got 0.5 because I'm doing 95% confidence, so this is my alpha.
Yep.
And in fact, actually, I can go even better. I can go 0.05. And then over here, I can go 0.01. Now here, I can go 0.001. And you can do something really fun. I want to lock this at A, but I do not want to lock the, I do not want to lock the row. And I want to lock this at 12, but I do not want to lock the column. So by doing it this way,
If I copy and paste this down, the 13 will change here, which is what I would like to do, but the 12 will not change, which is what I don't want to do. And then I can copy it to other alphas, and the B will change to a C, but the A will not change to a B. So I'll keep it over here.
this is you being able to make your own alpha and being able to make your own table. I'm just going to copy that down. And then copy it across. See, look at that.
Isn't that fun? And I have it for 15, 16, 17, 18. I made my own T distribution table. Each case, they're decreasing as the degrees of freedom increase, and they are increasing as alpha is decreasing. Because again, I have to cast a wider net to capture that true population. That's what I did for those who want to follow it. It's just this thing, and I copy paste it. It's pretty fun. So now you know how to work out any t-score at all. With just a couple of keystrokes. Don't have any questions on this? Nope. So let's go back to friendly friends.
I'm going to copy this whole thing. I'm actually just going to do it everything over here like this. It's going to get in my way. Okay, there we go. I'm going to copy this whole thing. Get in place. Now, I want to make that a T. And the only thing I'm going to change is I'm going to get rid of the norm part. I'm going to add a T. So now so I'm assuming that rather than saying, oh, I know the population standard deviation, I'm going to say, look, based on the average I got, this is the population standard deviation. Based on my sample, this is the population standard deviation. So this is the standard deviation. And based on the past.
Now, how do these margin of errors compare? Which one's bigger, T or Z? T, exactly. I mean, how much bigger are they?
About 10, yeah. Why does it make sense that they're bigger?
Why does it make sense that the T is bigger? Yeah, Rolanda?
Because T is less precise
Mm-hmm.
population.
Exactly. Exactly. We don't have that great information of signal. We have to rely on S, so we have less information, right? T, as you say, is less precise. So it gets a little bit bigger, right? If we want to claim that same level of
what's it of alpha. We have to do it. Now, what would happen? Oh, yeah, so
How did you, I missed that part.
a confidence is that confidence.norm to confidence.t. Right, so because I'm relying on the t distribution. I'm saying that 15,386, that's not population standard deviation, that is a sample standard deviation. Maybe if you're curious too, maybe I didn't talk to individual people, I talked to individual stores. And so that's how many that they will order on average. Something like that. What happens when I decrease that from 170 to something like 36, which I believe is, no, not 37. 37 is what I'm actually like. Now, which one is bigger, T or Z? T, the answer is always T. If you're asking which is bigger, T or Z, it's always going to be T. Unless you have infinite observations, infinite degrees of freedom, then they'll be the same. But here, they're always going to be bigger. But note that it got a lot bigger. This used to be a difference of 10, now it's a difference of 110. Why does that make sense? Mm-hmm. Exactly, we have fewer observations, so it's less precise on this part, right, on the end, right, which is why they increased, but they both have that end. But it's also less precise on this score as well, because we have fewer degrees of freedom, so this value went up. Also appreciate too what we were doing before. Look, no greater than 5,000 for that margin of error. A little bit less. And if you want to be tactical, you can put it into the 6.9 size. Any questions? Okay. All right, this one. Yeah.
Did you pass the signage?
Did I pass in the signage sheet?
No.
No. Oh, sorry. I set it aside. I'm like, I gotta pass that out, and then I forgot. I did. Okay. Let's switch gears. Recall how I opened this conversation of confidence intervals. I said 80% of people like candy according to surveys, plus or minus 5 percentage points. So 75 to 85% of people like candy. But what we've done does not involve percents. What we've done involves absolute numbers. You can sell anywhere from 0 to an infinite number of bears. But you can't have 110% of people like candy. That doesn't make any sense. So these percents, which are used for percent of people of a particular gender, or percent of people of a particular race, or percent of people who support a particular candidate, these are what we call proportions. So we have a different equation for confidence interval of proportion. I like the variety of colors, but I feel like I'm just going to switch to black. Calculating the confidence interval of proportion is a little different. To begin with, we need to determine the standard deviation of a proportion. The good news is it's pretty straightforward. P times 1 minus P, where P equals the proportion between 0 and 1, or the population proportion, I should say. Divided by n, and then take this further. Now, just as a side, we of course don't know
population proportion, we don't know P, that's the whole point. So we technically have to do this. Our best guess of what P is. P bar.
Where the hat is a reminder, this is approximation based on the sample. P bar is the proportion of the, that should say of the sample. I think I have this is the proportion of this.
Any questions so far? Now, what's interesting as this setup is that we are going to be using z-scores, even if we are estimating the sigma. In fact, note that this is not S, this is sigma. And we can do that because there is a maximum size that sigma can be for any proportion. For any value of n, there is a maximum size sigma can be. Does anyone know how I can say that? That seems weird. How can I say that? Anyone? If P is 0.1, what is 1 minus P? 0.9. Oh, what's 0.1 times 0.9? 0.009. If P is, I don't know, 0.3, what is 1 minus P? 0.7. What's 0.3 times 0.7? 2, 1. If P is 0.7, what is 1 minus P? 0.3. What's 0.7 times 0.3? 0.2. Oh, huh. That again. Well, that's probably a coincidence. If P is 0.9, what is 1 minus 0.9? 0.1. And what's 0.9 times 0.1? Do you see what I see? It went up, and then it went down. Suggesting there's a maximum. So what is that maximum? What is the largest it can be?
0.5.
0.5. Which means this is 0.25. You can kind of see this here, right? 0.4 gives us 0.6, gives us 0.24, and the 0.6 gives us 0.4, gives us 0.24. So the maximum that this can be, based on a particular n, is if you set p equal to 0.5. So sometimes we can do that. Rather than relying on the average, just say, look, the biggest it can possibly be is if we just set it to 0.5s, the most conservative analysis. And because standard deviation, the bigger the standard deviation, the less we know, that there's a maximum to the standard deviation, there's a maximum to how much uncertainty there could be. And that makes sense, because by definition, proportions are bounded between 0 and 1. So if there's a built-in bound, it makes sense that there's a built-in deviation. So, we have an equation. confidence interval for proportion equals P bar, rather than X bar. Well, we put this as P bar, the confidence interval. P bar. We're going to be taking plus or minus, just as before. Z alpha divided by 2. And then we multiply by this. Or by that, technically. P bar minus P bar all over F. Note, again, we're using the z-score. So, that equals 36, and P bar equals 0.8. You know, 80% of people like candy. And we like to know as z alpha divided by 2. Let's see, do I want to do 99%? Let's do 99%.
I was in really fun. Let's do 99%. So that would be 2. Let's do 99.9. That's a better number. 3.291. We can determine a margin of error. So you can, of course, just put this into Excel and type it out. Excel does not have confidence.p built into it, but this is a simple enough math you can do it. So what is 0.8 times 1 minus 0.8? I think I heard it. Because 0.8, 1 minus 0.8 is 0.2, 0.2, 2 times 8 is 16. But then you got 2 decimal points in there, 0.16. N equals 36, square root, and then 3.291. So that's our margin of error, and our margin of error. And then this becomes 0.4 divided by 6. Times 3.291. You did that in your heads, right? Square root of 36 is 6. Square root of 0.16 is 0.4. Same story, square root of 16 is 4. But, you have decimals in there. And then we can take 6 divided by 3.291, which is going to be making me perform 0.5, 4, that is 24, 5, 1, 51, 6, 51. What is that about? I'm blanking here. 8. So it's roughly that. That's 0.4. Is that right? I'm doing my math right so far? And you should get something like
0.21, which admittedly is pretty big because we're going to take that 8 plus or minus 2.91. So obviously this maxes out at 100, and then the lower value would be about 6, a little less than 6. So our sample size is admittedly kind of bad because we have our margin of error is so large, it's exceeding the 100%. And most importantly, too, we're going anywhere from 60 to 100% of people like candy. That's like kind of bad. It's like, well, it's more than half. Like, great, thanks. Okay, last thing, quick math for margin of error. I'm sorry, optimal sample size. Maybe I'll let you go because I'm going over here. I hate going over.
So I'm just going to write it down quickly. You can, of course, do the math yourself if you want to verify that this is the way it works out. This is the very last thing.
It should be n equals z alpha divided by 2 over me squared p average 1 minus p average.
So if you're trying to figure out, well, we don't want anything more than
Plus or minus 0.03 or 3%, how many people do we need to survey? At say 95% confidence or 99% confidence. And then you can figure it out. Again, you can use 0.5 in order to maximize that.
okay. All right, I'm going to let you go. I will see you then on Thursday. Have a great couple of days, everyone.